technical because I was told it's going to be a general audience. But I still couldn't escape putting a couple of technical slides. But at any point, if you just feel free to ask questions. The aim is to try and, at the end, I just hope to say that the verification problem as of today is nowhere near being solved, and my belief is it's unlikely to be solved for a very long time. We will see why I believe that. So I'll just give a very brief overview of one of the techniques that I use for verification, static analysis, and multi-cheating are the two techniques I will really be talking about. What's the current state of art in terms of what can be analyzed using the modern tools and current technologies that are available, how much can be analyzed, and take a look at what needs to be analyzed, what's the requirement from practitioners and users of this technology. And that's the general theme of this. Is verification critical? It's necessary in many ways. There have been all kinds of software bugs. I haven't put his favorite Arjun Mishra because that's very old. And there are a lot of fairly recent problems that have been there. And I've taken care to put a whole variety of domains. It's not just the safety critical domains, but even in the non-safety. So Amazon sold items at 1 pence each. And there have been such cases for airline tickets, there have been these things, Nissan, Airbag, Knight Capital bought and sold shares at huge loss. So it's not just, there is this general belief that only the safety critical industry needs verification, which is not true. And it's every industry that needs to, because the losses are pretty heavy. The safety critical, it's also costs life. So that's why there is a need for. So it has been the top 3 causes of medical devices recalls. In fact, medical devices recalls have been so bad that people have, with the heart implants, have been called back to remove the heart implants because there was a software bug that was detected. So in case of vehicles are recalled, but when you start recalling heart implants, it becomes even more severe. Here is another crack at the cost. This is just last year, and this is a cost estimate that has been arrived at from just assessing losses caused from newspaper headlines, what could be made out from newspaper media headlines. It's not really doing a very detailed analysis. The actual loss will be more than this. Here is what you just looked at newspaper headlines. And again, you can see it's a whole range of domains that are facing problems because of software related bugs. And these are only talking of software defects that have caused some loss of the. So verification or trying to detect software defects or bugs is definitely very important from not just a safety critical perspective, even from a financial cost perspective. And things are getting fairly complex. Today we are in a much, these verification problems are in a much easier world. What is going to happen is far worse with autonomous vehicles coming in where you don't even know what's the verification problem. The Tesla car crash, if you are aware of, is because it didn't recognize an object correctly. It didn't recognize a tree as being a tree or a wall as being a wall. It's now how do you even define what's a wall or what's a tree? How do you define correctness in those situations? That itself is a challenge. Plus, checking or analyzing for them is a even harder challenge. Complex surgeries are being performed by robots. In fact, there are eye surgeries which can be performed only by robots. Humans just can't do them because of the precision that is needed to perform those eye surgeries. And rescue operations are widely carried out by robots because, again, it's just the situations are quite too dangerous for humans to get there. And therefore, and decision makings. In the trading industry, already the trading loss was because of the software glitch. Already a whole lot of decisions are made by algorithms. They are less made by humans. Quite a lot of humans. And there is even more complex decision making that's being made by algorithms. It will be, the future is not far when many war decisions may be made by algorithms. So there are all kinds of decisions that will be taken by algorithms rather than humans in the future. So the future, the software is getting far more complex, and the verification challenge is already costing us quite a loss not today. So it's a very important problem to be addressed and looked at. Yeah. So for today's talk, I'm just getting the terminologies clear. This terminology itself one can debate, but for today's talk, let's just take these as definitions. I'm looking at proving as when you are given a application and you're given a requirement and you show that the application works correctly with respect to that requirement. So software meets requirements I'm looking at as the proving problem. And testing is you're given a piece of software, you generate some sample runs for that software, and then you check if the software runs correctly for that set of runs that you've given. That's what I'm looking at as the testing solution. And then there is verification, which is you're given a piece of software and you're given a bunch of properties, and you're checking whether the software meets those properties. This set of properties, in the most extreme case, can be the entire requirements, and in the most trivial case can be just one or two properties. It can be anything. So that's the terminology, just for the purpose of this talk, that's the terminology that I'm going to use. So, proving is you've got a bunch of requirements, typically in natural language, and quite often in the heads of people, domain experts, they have it in their heads. And then you have two parallel implementation of it, one using some formal notation, which is hopefully in a language which is far less complex than the implementation language, and therefore more readable and likely to have fewer bugs. And the other one is implementation, which is in some programming language, and much more harder to review or understand. And you just want to show equivalence between the two. Other advantage of the formal specification is it doesn't need to satisfy non-functional requirements like performance or usability. So you don't really care about those requirements in the formal specification. Although even they become important because we'll not get into that. So formal specification is there. And you want to show that they are equal. That's the proving challenge. And this is quite impractical for several reasons. It's undecidable, of course. It's undecidable in the general case. For large systems, it's not even possible to come up with complete requirements for large complex systems. Nobody knows what the complete set of requirements is. For an operating system that we use daily, nobody knows what's the complete set of requirements is. There is a bunch of typical scenarios on which we work. And in many cases, people may not even care what the complete requirements is. The implementer may bring in some requirements which may not really be a concern. So if you have your mobile phone, it behaves, after a few button clicks, it behaves in a certain manner. Nobody cares whether it's right or wrong, what is right or wrong. So it's not even, the complete requirement is not even so. And creating formal specification is often as expensive as coming up with the implementation. Because finally, you have to get the complete specification in a rigorous formal form, and that's going to cost. So that's as expensive, comparable cost as coming up with the implementation. Implementation may cost a bit more just because of it has to give in other attributes like performance and others. But otherwise, you're doing the same problem, you're solving the same problem. And some may even argue that a programming language is a formal notation, and so you're just writing it in two different formal notations and comparing. But there's no reason why one should be much significantly cheaper than the other. So that's the challenge with Proving. Testing is the most practical everyone uses testing. There is very little they use other than testing. And wherever you go, whichever industry you get in. And it guarantees almost nothing. It only says that I have run it for this bunch of examples and it works right for these bunch of examples, and it's very likely to work on all similar examples. And but beyond that, we don't know what will happen. But it's the most practical. It's the most widely used. In fact, one can say it's the only thing that's used. There are small pockets of things that go beyond this, but 80-90% of showing correctness of software functionally or otherwise is through testing, and that's mostly. And testing has the other challenge, which is having run it to check is it run correctly is hard, because otherwise one can always, generating test cases per se is not so hard, because you can always generate randomly. You let a random number generator, random input generator run for days or weeks, it will generate a whole heap of input, but what's the correct run for that, what's the expected result for that is not easy to get, and therefore that's hard. So to restrict that number of data, they try to get in whole definitions of coverages, saying that we have tested for all requirements, we have tested for all branches, we have tested for all statements, whatever it is, some coverage criteria. It's just that all of it.
So understanding, so it's a common specification for the implementation. So that common specification you expect program at that level, or it is somewhere.
So it can be, when you are trying to prove a program correct, it has to be to an extent where it's functionally complete. You can decide that I don't want to really care about the program, that's what typically people will do, which we come to the properties, to look at the critical parts of the program and look at only the correctness for, with respect to those critical parts of the program. That's what they typically do. As difficult, yeah. That's the only example I've heard of in all my life where the specification is easier than that. Now, even if you come to the sorting program, take the specification, write a formal specification for permutation. Sorting program is not just about sortedness. It's about permutation, the result. Right, so now you write a formal specification in some language for it. That the count of every element in the resultant array is equal to the count of. That's the easiest. Yeah, it's much easier than the algorithm, I agree. But there are a few such small examples where sorting is one classic example where specification really works out much easier than this thing. Minimum is another, but minimum the code itself is fairly easy. But even if you get into things like second minimum and all, the specification starts becoming harder, and not just harder, it gets harder to convince oneself that it's the specification of second. You have not missed a particular case. And when you get to large programs, quite often when you get into a large program, large parts of the programs are doing something very simple. And for those simple parts, the specification and the program there is virtually no difference. And so that's the kind of places where it really starts creating problems. But even for sorting, I can tell you, if you give a person to program it and another person to write the specification, the time difference will be reasonably comparable that they take, assuming someone knows what the sorting algorithm is. Someone knows the sorting algorithm, they won't take too much time to code it correctly, as a specifier would take to. Correct. Oh, there aren't too many. You can try. There aren't too many examples where the specification becomes easy, much easier to write than. What makes implementation really hard is when you start bringing in performance. Sorting also, it's the performance that really makes it hard to implement rather than. So that's the kind of things that then you have to start doing all kind of tricky things quite often. Yeah, I agree. I agree. I agree. But when you get into a large application, no, the components for which you need to do those tricky things become small. The percentage of the application for which you need to do those tricky things are now small. Like if you take a Windows NT, 40 million lines of code, the number of pieces of code in that where you need to do tricky things, only in thousands, tens of thousands. It won't even be a million. And therefore this gap becomes much more. Because a lot of, in these large applications, a lot of code is just routine code. It's not really complex. And verification, as we have defined for the day, is you're given a bunch of properties for a program, and you check whether the program works correctly with respect to those properties. You really don't care beyond those properties. And that can be critical because you could just specify some of the critical properties of a software. You don't need to look at all the properties. Again, it needs a good list of properties. Getting a good list of properties is a big challenge. And it's even for all kinds of programs, it's not very easy to get a good list of properties. And therefore, people fall back to very general programming language specific properties to verify. Scalability and precision are the key challenges. So, as an example of verification, this thing you could have very platform or generic properties, program language specific or platform specific properties that are very generic, like deadlock detection is a more OS specific property that you have. And here is an example where you are just checking whether there is a divide by zero out here, and so is there a divide by zero out here? This is all you are checking. And the reason I put this up is to illustrate that even for such a small three-liner, it's hard for us to visually verify whether the property holds or not. So here, it's not really trivial to check. I've carefully made that a non-negative integer to have a look for a divide by zero. And so if j is less than I, you have a j prime gets I, otherwise j prime gets j plus 1. And because j is less than I, both are non-negative, 0 is going to be, I is going to be, j is going to be 0 or higher, and I is going to be greater than 0, and you are assigning. So that's the argument one typically uses. But in the presence of overflow, at this point you can have an overflow in a standard programming, and it can become a 0, or it can become a divide by 0. So there are these tricky corner cases which one can very easily miss when one is doing it manually, even for trivial examples like this. You could also have very domain-specific properties. Once you are looking at properties, you could have any property, like a car should stop, a vehicle should stop within t seconds of braking, or a debit for a financial application, there should be a debit entry for, if it's a double entry system, it should have a debit entry for a corresponding credit entry, and don't sell at a loss, or don't sell at as a more than certain percentage of loss. Can be to avoid those kind of trading disasters, you could have a thing which says never sell at a loss which is more than some percentage or something like that.
but in integer it is not. So if there is a document, something happened. So that is
Yeah, so typically what you want to do is see that there is no overflow.
but if the overflow is defined, then you can do that.
If the overflow is defined, you should be able to, someone may explicitly use the fact that, in fact, I have seen real life code where people do use the fact that overflow is defined and it just translates to something. Yeah, so they do use that. Then in which case you don't want to flag it as an error depending on the property. So overflow by itself may not be an error, but there should be something else down the line which could be. You're right, there are all kinds of these tricky issues that are there when it comes to verification. There are pieces of code where programmers have coded overflows, wanting it to overflow, and use the result of the overflow. So soundness, scalability, and precision are the three key challenges when it comes to
This is just a little bit of a side note, because the overflow reminded me. Apparently, in the US, some 2 or 3 years ago, they have a time model that is called network services, and the state of Washington, because of overflow, there was an error with time model calls not being routed.
something like that. I also remember having read this.
And the only fix was someone went and changed the.
Reset there was some counter which overflowed, they went and reset the counter.
That company was unfortunately not located in the same geographical location, it was connected or something like that.
I recollect having read this news item. They had to just go and reset, they didn't know what else to do. And someone said, you'll never have so many something. Yeah, I recollect having read that. So it's all very, so these are the kind of things that really make verification tricky. In some places the programmer intends it, in some places it's a bug. And to be able to, that brings in a whole heap of precision problems. And so precision is a big challenge. Soundness is when you're not going to miss any of the bugs. Precision is when you report something as an error, what percentage of it is genuinely an error, how many of them are false alarms. And scalability, of course, is what's the size of application that you can analyze. Precision is a key challenge. So in our example, we have a static analysis tool. We've been able to detect for a program, you can show that for a certain set of inputs, it will definitely crash, let's say. But the programmers will argue that, but this set of inputs will never come. It's something which you don't know for the given program, because that's an environmental constraint. But they say that this set of program errors will never come. So you need to, when you're addressing the program analysis problem, you need to even look at that. Or you have some library code for which you don't have the code, and they will say, but this function will never return something like this. Whereas your analysis, if you want to be sound, you will want to start. So precision is one of the harder problems which makes most of verification unusable from a practitioner's perspective. Practitioners don't want to use because they don't really want to analyze all these false alarms. And the general belief is that you try to achieve one, you're going to compromise on one of the other two. If you try to achieve scalability, you're going to compromise on precision, or soundness, you're going to, and there are all kinds of stance people have taken. Some have said we have to be sound, static analysis community is one. There are a whole heap of heuristic-based analysis which looks for patterns of common user errors to be fast and precise, but you miss out on a lot of bugs. So that's the key challenge in verification, is how to be highly precise, be as sound as possible, and high scalable as possible. So I'll just take you through a couple of examples. Static analysis is one of the earliest verification technique that's been around, which is the problem is it's very throws up too many false alarms. The way it works is it creates an abstract model of the program. And when we say abstract, what we mean is the abstract model allows more runs of the program than the concrete model does. So there are more runs of the abstract program than there are of the concrete model. So, and because there are more runs of the abstract program, there could be more runs that may lead to an error. And many of those will not be present in the concrete model of the program. And that's why it generates too many false alarms, but it's very scalable. Of course, there is something called abstract interpretation in static analysis, which tries to improve precision great deal. So Kuzo and Kuzo are pioneers in that. And so depending on, for every domain you can come up with an abstract domain and make the whole thing very precise. So for example, Airbus, so the Kuzo are French, so they have a lot of collaboration with Airbus, and Airbus claims that one variant of their aircraft was fully verified. So they had shown that it will have no crashes of one bunch of categories: division by zero, anti-index on a bond, overflow, underflow, this whole heap of categories. And they had used only static analysis with abstract interpretation. Of course, the kind of abstract interpretation they have tuned into it was very customized. So they used to run, find a problem, put in an abstract interpretation, abstract domain, rerun. So it was highly customized, highly created for that particular application. You go to something else, it will start to at the whole scale or global something. More recently, what has really caught up are SAT and SLT solvers. They have really scaled up, and SAT is SAT problem is known to be NP complete. This was the first problem that was shown to be NP complete, in fact. And currently there has been a lot of scale up. I'll have a chart on that. And so, as I said,
At a previous slide, actually, when you say false positive, false alarm, is it due to the abstraction or it is due to the number of runs that you have?
it's due to the abstraction. It's only due to abstraction.
The also that a number of runs actually become many as
Yeah, so that's the number of runs become many because of abstraction. So here, so what's an abstraction? So here, for example, one way they will look at an abstraction is instead of looking at all values of I and j, they just treat I and j as 0 or greater than 0 as only two sets of values. So that's an abstraction. So that won't capture the plus 1 very precisely. Plus 1 will take you from 0 to positive, or it will from positive it will retain you in positive.
I think it is difficult to visualize how the number of runs will increase that. Because if I have a complete program, then I will differentiate between 0, 1 and 2 and 3.
Correct.
If I have abstract program, then I will have the 2 classes or 3 classes.
Correct. So therefore there could be, for example, if I have an I less than 5, if I model the I as just 0 and positive numbers, I may say I less than 5 can be true or can be false. Whereas in an actual run, I less than 5 will be, for certain runs it will only be true or only be false. So with an abstract program, both are possible. In a concrete program, only one of them is possible. So an abstract program gives you more runs than a concrete program does. Or taking a very trivial example, assume my program is just I equal to 0, j equal to I plus 1, and whatever. That's it. Let's assume that's the only one. If your abstraction is just negative or non-negative, now I can take any value, j can take any number of values. Whereas in the actual run, I can only be 0, j can only be 1. I'll take a very trivial example. Okay. So this is the main thing. It needs to know many theories. If you want to do a whole heap of abstract interpretation, it needs to know theory of integers, theory of positive numbers, theory of modulo numbers, all kinds of things when you, depending on the kind of programs that you have to get precision. And that's what is really makes it. So here is a simple abstraction. You're just looking at whether J can be 0 or non-zero. And yeah. So is static analysis useful? So we conducted abstraction and over approximation are synonymous. Abstraction and approximation are not. Over approximation and abstraction are synonymous. Abstraction and approximation are not. Approximation could be unsolved also. Over approximation, they are usually used synonymously. Yeah. Yeah. They are normally used synonymously. One community uses the term abstraction, another community uses the term.
That's what the problem is. That's what systems we are discussing.
Yeah. Over approximation. Then that WSSC, the discussion was soundness.
No, not about that. Also about abstraction.
Over approximation. Yeah, we can discuss that offline, but they are used synonymously. So now, can static analysis help? So this is we conducted a couple of experiments in TCS where we took actual applications. Fortunately, our customers were willing to share with us data on the defects, and they also spent effort in categorizing those defects as what was the programmer mistake that really caused the errors. And this is the kind of things that we really found. So more than 30% of defects could have been caught using static analysis. Just simple plain static analysis. That's the finding that we got from these experiments. For the two systems that we analyzed were, one was an office automation system where we actually only analyzed post-production defects. Defects that were reported from the field. What were the defects and how many of them could be analyzed? And we found that if they had used a static analysis tool, they would have saved around $1 million per year. That's the kind of effect. This doesn't even take into account this is just the cost of software development and fixing. It doesn't take into account the cost of recalls, it doesn't take into account the cost of brand loss, none of that. Just the cost of defects which is fixed. Similarly, the other system we analyzed was a vehicle infotainment system. And we found out that around 68% effort could have been saved in review time if they had used a static analysis tool. So there is practically there's value that static analysis can bring in to the industry. Abstract information, right? That's true. And when we measured this effort, we took into account the review effort to analyze for false positives or false alarms. Taking into account all that effort, we actually measured how much time people take to analyze a false alarm and what's the kind of effort that's needed. It's taking into account all those efforts. Those are the numbers that we use. Again, here are results of experiments of doing static analysis. These are all applications we have really run off. This is the same infotainment system. So it has some 77 zero division warnings. And one can assume, nobody's analyzed all of them, but one can assume most of them are false alarms. Because it's a production system, it's well-tested production system. The chances are most of them are false alarms. Less than 5 of them will be genuine. And you're looking at a 2 million line of code. So you can imagine to verify whether it's a false alarm or not, the kind of expertise and effort that's going to take. So here is the key challenge that you have. And here are some samples of code that you have taken from, snippets that you have taken from these examples, where we are really looking at. We have cleaned up the code a bit. So when I say j equal to random, it means there is some complex computation, but there is a multiplication by 2 that happens. And there is an array being indexed, array of size 5 or 2. And so it will never enter here for 5 on 1. That's the key, because it's being incremented by 2. And you start from 0, so it only goes through even numbers. So j will never take a value 5 on 1. That's what the programmer is relying on when they wrote this piece of code to ensure that there is a no array index out of bound error. So abstract interpretation can catch it if there is an even number domain that the abstract interpreter implements. And mostly nobody will implement an even number domain, and therefore no abstract interpreter. And here is another weird piece of code that is really given a large integer, trying to compute the year, month, date of the that it's representing. Given that it is times and something, it's trying to figure out.
So why can't it be 5 years and 1 month? The j tree can take a whole value also.
J, no, that's why into 2 is there. So it can only take an even number. So these are kind of pieces of code that really pose challenges to all verification. So here, of course, it's impossible to solve problem because someone has got seconds for each month of the year encoded as integers, and they're reducing the seconds and increasing the month, and you have to show that there is no array index overflow. Unless you analyze the entire array, you just can't figure out that there will be an overflow. There is no math that's going to help you solve this problem. And unless you have very deep domain expertise, and you also know what the seconds in each of the month are, and you validate each of the month second. So these are the kind of hard problems that a verification tool has to really face. The other thing is, as I said, SAT solving, where you convert an entire program into a Boolean program. I'll go slightly ahead. SAT solvers are really scaled up of late. So this is taken an exponential performance. It's an NP-complete problem, but very well engineered tools are available today that can do the SAT solving. But they also fail in the presence of loops like this. All of SAT solving fails for such loops, and this one they may be able to solve because you just have to unroll the loop 12 times. That they may scale up for. But these are things for which, because this is an infinite loop, theoretically infinite loop, and this is a large loop, 512. There could be much larger loops for which we can. So I'll come to some of the works that we are really doing. So this is an example that's from a device driver, Microsoft device driver, which was published by Sriram Rajamani and others as part of their early SLAM work. So here the main point you're really looking at is state should not have the value u at this point of the code. And the question is to be able to analyze this. It's a loop which is there, and there are various techniques that have been applied for this piece of code, and we will look at one such technique. So if you really look at this code and you assume there are only two blocks. There is this block of code and there is this block of code. These blocks will get executed in a unit. There won't be any smaller lines of code in which which are getting executed. So if you look at any run of the program, it's going to be of this form. There could be several B1, B2s, and then followed by a whole heap of B1s, 0 or more times. Right? So there is always a last B2 which gets executed, and then there is a last B1 that gets executed. Correct? So, as far as you are concerned, this is state not equal to u. So you just need to analyze the last B2 that's getting executed, because that's the only one that's really assigning a u to it. So you need to analyze, figure out what's the last B2 that comes. And look at it more carefully. State is the only variable that's visible beyond this loop. Because none of the other variables are really being read after that loop. And therefore you need to look at only the last iteration, because the last iteration is going to assign to state. Okay? So it will be, the last iteration will be either B1, B2 or just B1. Right? Now if you look at it from this perspective, last is B1, B2. Now if it's B2, NP gets incremented. Therefore, it will re-enter the loop. NP not equal to NP0. Because there is an NP over equal to NP here and you are getting incrementing NP. It will re-enter the loop. So it will never come out of B2. So if it comes out, it will come out only of B1 and where state is it. So the point is, you need to analyze only one iteration. Really. You don't really need to analyze all the iterations of the yeah. So that's what we really do in an output abstraction. This was a simple example, but there are a lot of other examples where you just need to count the number of output variables, in this case 4. So at most you would analyze 4 iterations of the loop. But if you're slightly smarter, you just need to number of unique blocks modifying pure outputs. And you would analyze that there is only one unique block modifying pure output. So in this case, we need to analyze only one iteration of the loop. So we transform that loop to having only one iteration. And of course, we have to make the inputs to that iteration abstract. So it should take in, the input should take any value of the previous iteration. So we make it, we assign non-deterministic values at the beginning of the loop, and then analyze only one iteration of the loop and check. And because this is an abstraction, that is, it allows more runs than the original program, if this says there is no bug, there will be no bug in the original program. And if this program says there is a bug, you really don't know. You just throw up your arms and say, we don't know. And you can get into a refinement, modifying the That was a case where the assertion was outside the loop. When the assertion is inside the loop, then we use induction. So here is an example where the assertion is inside the loop. And it's an infinite loop, while there is a assertion that's getting inside. So what we do, we use the same abstraction that we did earlier and get a, so the base case is of course easy to check. We just check it for the base case of an induction using that. The hypothesis, we just take a assertion inside the loop and change it to an assume, which says that do not consider runs where the assertion is violated. Consider only runs where the assertion is not violated. That's what the assume really says. So we take the assume, and then finally we have the assertion outside the loop, which is to validate the hypothesis. So this is the hypothesis case, and this is the checking of the property. So when the assertion is inside the loop, you use induction to be able to do all that. And again, you can see that we have reduced the loop size to just 1. And therefore, a model checker can now scale up to be able to do that. And then we just use a model checker to verify this part. So this example also can be verified using the because the number of unique blocks modifying a unique set of variables is 1. That's why we have absolutely. Now the natural question is, does this really help in practice? So we took a whole heap of real life applications from various domains, automotive, there was a free scale application, there's all kinds of applications here. And this is the sizes of these applications, 8,000 lines to 171,000, 184,000 lines of code. And all we did was abstract out these loops and then applied a model checker to be able to do that. And these are the static analysis alarms. That is a normal static analysis tool gives as alarms. And these are the reduced number of alarms. That is, after having used a verification tool like this, what's the number of alarms reported at the end of this? And this is the percentage reduction. This, of course, is just this divided by this.
So these alarms are false and true.
They are both false and true alarms.
So how do you measure?
We don't know. But we know that the ones that the lab MC has eliminated are definitely false alarms because it's a sound technique. But the remaining 21 we don't know. Like, so we have percentage precision improvement assumes that all of them are false alarms. And,
So it actually can be even better than this.
it can actually be. It will be much better. And this is the time. That's the main thing. So we are really taking a lot of time. Although it's per alarm we are taking around 1 minute, which is quite high considering that the total number of alarms is pretty high. So 300 alarms and 402 alarms are pretty high. And we also compared it with other, this is slightly dated, this is 2 years old, 2 to 3 years old. So all these tools have improved in the meantime. So you can see that most of them don't scale up. And even we do only 131 out of 186. We really don't do all of them. So there is still a whole heap that needs to be done.
So
CBMC is it just unrolls every loop and it just becomes real. There's no abstraction. So it's all the other tools do abstraction of something. And CBMC is the one that doesn't really abstraction. And but I have to admit that we use CBMC. Yeah. So the next interesting problem is arrays are another problem. So if you look at this standard minimum program and you want to see if there is a specification for minimum, is this correct or wrong? The intuition here is, this of course is a hard program to analyze because it's got a loop and an array, which is very hard to do. So the intuition is, all you want to check is whether there is some element k for which ak is greater than or equal to minimum. For that, you need to analyze only the iteration in which ak gets assigned. AK is read out. That's the only iteration you really need to analyze. You don't need to analyze any of the other iterations. So the question is, so if you do that, you can really reduce it to this loop where you look for only one element, ai less than min equal to ai, and assert ai is greater than or equal to min. You can show that the minimum program is correct by just analyzing this much, completely getting rid of the loop. Yeah. And you have something similar here. All you are doing is counting the number of zeros in an array. And you are asserting that the count is less than 3. Now, if you want to verify whether the count is less than 3, you just have to pick the 4 bad elements in the array, or 3 bad elements in the array. If all 3 of them are 0, then your count is, so you just have to pick 3 elements of the array, 3 arbitrary elements of the array, and show that the count is 0, right? So you just need a k as 3, analyze, pick those 3 arbitrary elements. These are 3 arbitrary elements, k as 3, and check for those 3 elements. Since these are arbitrary, if there are 3 elements with 0, those will get picked, and your count will be greater than 0. So that's a good question. So what we have shown is that to find a k, if you can check that for every k loop, if there's a k plus loop and the property holds, that is for all k subindexes of this thing, if for k plus 1 also property holds. So you're looking at k and k plus 1 as 2 small finite loops, and we run CBMC to check that. If this holds, then you can shrink the loop to size k. That's what we have shown. Yeah. So you can determine this given any loop, because these are all finite, and it uses modern model checking, so it uses a small amount of k. So we go from k equal to 1, 2, 3, 4, and stop when we can. If it doesn't scale up, we give up. And so that's the array shrinkability, k shrinkability thing, and we work for only k elements of the loop. Yeah. So we put all these together in a tool, Variance, and participated in this SVComp competition. We did last year too, and this year too. And so the loops, and this has been our prime focus because our entire work has been only on loops and arrays. And so not surprisingly, we finished first there. But surprisingly, the other categories too, the overall read safety category also, we finished second. This is something that had around 21 tools that are competing in the competition. So now the last slide. So reality check. Where are we with respect to verification? So verification of 1 billion lines of code, let's assume we can do, which is not really true, but let's be kind and say we can do a million. And we can do primarily sequential code. Concurrent code is a completely different ballgame. Modern cars have billion lines of code. A modern BMW or a Mercedes-Benz has a billion lines of code, doing all kinds of really fancy things. And it's got more than 100 ECUs, which essentially means that they are highly distributed. So it's not a billion lines of sequential code, a billion lines of highly distributed code. So the gap between the current state and what the current state of technology the practitioners are requiring is huge. The gap is really huge. We are nowhere near being able to get that gap. And add to the fact that today there are sophisticated algorithms like image processing and others where we don't even know how to state a property. If you want to verify image processing, we don't even know what's the property we want to state. And so that makes it that much more harder. All autonomous vehicles, they'll have all these problems. When do you decide whether it should brake or not? That is as hard a problem as a machine learning problem. So things are really bleak in terms of verification, where there's a really long way for the verification technology to catch up, to become practically useful, and to try and make a dent on the kind of losses that are there because of software errors. And that's the reason you're seeing so many losses or loss of lives or whatever because of software errors, because there just isn't available technology to be able to check if a piece of software is going to work correctly all the time. And the gap can clearly indicate that I don't think that technology is going to come anytime in the near future. So still a lot of research is needed, a lot of great earth-breaking ideas are required to be able to get there. That's all. Thank you.
Any questions?
What section of the... So, like I said, this is much worse than multi-threaded. 100 ECUs is message passing. It's distributed, not just multi-threaded. It's much worse.
So if it was entirely the large factors, one scription program, then they would be within reach.
Yeah, it's a billion lines.
Right now the standard is
Being very generous, it's 1 million.
1 million. I said 10.
A million lines of code.
Oh, never is.
That's also being generous. Even million, I don't think most tools will scale up. You know, they may analyze 1 million line of code for one property or something like that. It is being generous, but it's a billion lines is just
You are statically analyzing a sequential program to find the pattern, for example, in Python, you can shrink it so that you can apply knowledge. Parallel program, do you work where you statically analyze the program to find out any pattern so that you can limit the number of threads or the number of processes so that
do we do that? Not really too much, but we have initiated work on that. There was one work where we had looked at invariants on variable data dependency to see to